Okay, so today we're going to look at chain rule and related rates again. We're going to look, these are applications of derivatives, so we're just going to revisit these. Again, the related rates is to deal with relating rates to each other. Okay, so this is just like what you would do in chemistry or physics. We're doing rate analysis. And this is related to the chain rule, how we apply the chain rule. Okay, so to do these problems, we want to first of all relate the variables in the question to the problem. So whatever the variables are that are in question, you want to try to come up with a formula or some kind of relationship between those variables. And we want to treat those variables as embedded functions and generally as a function of time. Okay, so they are embedded functions of time. So we can then, when we differentiate them, we can use chain rule to differentiate them. And then once we differentiate these using chain rule, once we have this new differentiated expression, we can start plugging in all the parts to solve for the unknown parts in that expression. So we'll do an example here where we have a sphere growing at a rate of, the radius is growing at a rate of 1 centimeter per second. So imagine some air being pumped into a sphere, and that sphere is going to grow. And it's going to grow at a rate of the radius 1 centimeter per second. So we need to figure out how much volume is being added in, or what rate the volume is being added in, okay, when the radius is 5 centimeters. Okay, so, and just to give some context to this, when it's really small, if you want to grow at a rate of 1 centimeter per second, you'd have to add a very little bit of volume. Whereas if you have a big sphere, you'd have to pump in a lot of air to make it grow 1 centimeter. Okay, so first things first, we need to relate the radius to the volume. Okay, those are variables. And we have a formula that does that. Volume is equal to 4 pi r cubed over 3. Okay. Once we have this, we're going to treat volume as a function of time, the radius as a function of time, and differentiate these as if they were embedded functions. Okay, so we're going to differentiate the cube. Once we hit the r, we have to apply the chain rule. Okay, and since r is a function of time. So at this point, what's left to do is we just have to figure out, okay, what are we looking for? We're looking for this piece here. Okay, we're looking for the change in volume with the change in time. We need then the radius and the rate of change of radius. Well, we have both of those. We have the radius, 5, and we have the rate of change of radius. So I'm just going to plug those in. And I'm going to plug those in using the units, because it's important to see that the units actually work out. So I have 1 centimeter per second. So when I multiply this all out, 25 times 4 times 1, I get 100 pi. And this is centimeters squared times centimeters is centimeters cubed per second. Okay, so the units work out as well. Okay, so looking at a similar problem, well, same situation, but now we've been given the rate of change of volume, so dV by dt, and we want to know the rate of change of surface area, and you're given the radius. Well, we need to connect the volume to the surface area. That's we could do that directly, but that's kind of hard. But really the radius and surface area are connected through, the volume and surface area are really just connected through the radius. So I'm going to come up with the formula for volume in terms of the radius. And I'm going to come up with a formula for surface area in terms of the radius. So 4 pi r squared. So what we're going to do then is we're going to differentiate these with respect to time and see what we end up with. So we're going to get dV by dt is equal to 4 pi r squared, and multiply that by dr by dt. Okay, we're going to do the same thing here. The change in the surface area over the change in time is equal to 8 pi r times dr by dt. Okay, so what we have here is we know that dV by dt, we know the radius, we don't know dr by dt. Okay, but we could solve for dr by dt. Here we're trying to solve for that. We know the r, and we don't know the dr by dt. But since we can solve for it here, okay, so I'm going to plug in 20 centimeters cubed per second, 4 times 5 centimeters squared times dr by dt. We can actually solve for dr by dt, and then we're just going to plug it back into this side. And that allows us to solve for ds by dt. So we get 100 pi centimeters squared, and we're going to divide on that side. So we're going to get 20 over 100, which simplifies to 1 over 5, and the pi goes down there. That becomes centimeters cubed divided by centimeters squared per second. That is our dr by dt. Well, we can take that and we can plug it into here. And now we can solve for our surface change in surface area over change in time. And then we end up with, this is going to be 1 over 5 pi centimeters per second. Okay, the 5 and the pi's cancel out. We end up with 8 centimeters times centimeters is centimeters squared per second. So the change in surface area and the change in time is 8 centimeters squared per second. Okay. Now, we could have directly connected surface area to volume through the radius. So we could solve for the radius here, we could solve for the radius here, made those expressions equal to each other. But we would have gotten kind of messy expressions there. So it's much easier to do it through the radius rather than solving it directly, volume equaling some expression of surface area. Okay.